Hi there, Dr. Tashan here, and in this video we're going to take a look at the epsilon delta definition of limit. I'd like to preface this video by letting you know that I have made previous videos on the informal definition of limit. I've made videos on the graphic representation of limit, and then I've made analytic representation of limit, especially indeterminate form, and I've made those as well. But we're going to now look at the precise definition of a limit, the formal definition of a limit. What else is it called? The epsilon delta definition of limit. So let's take a look at this definition. Okay, so just remember with limits, when you start a calculus class and you start studying limits, you're going to look at functions, and you want to, as the x's approach a number from the left and the right, you want to see where the y values, where the function values are going. Okay, so limits are all about where's the function going. You never have to get to that spot, but where is the function going? Okay, so the informal definition says as the x's get arbitrarily close to a c value, as you approach from the left and the right, you get close to a c value from the left and the right. But mathematicians, they want so much more precision. So you're going to get close to a value from the left and the right. How close are you going to get? All right, so how accurate do we need to be? So the epsilon delta definition gives a little bit more preciseness to how far away, the windows need to be, how far away you're getting from the left and the right on the x-axis versus where the y's are going. So let's take a look over here on the screen. Here is where the definition is. So f is a function defined on an open interval at interval that contains c but not actually at c. You can have a limit without a function value is what this is saying. So the statement limit as x approaches c of f of x equals L means for every epsilon greater than 0, you're going to have a delta greater than 0, such that you have your inequalities here with each of the x and the y windows. So looking at the diagram, you want to take the limit as x approaches c from the left and the right. Okay, so as x's get closer to the c value from the left and the right, we want to see where the y's are going. But as x's get arbitrarily close, well, how far is arbitrarily close? So we're going to actually get a size of a window, if you will, so we can see a little bit of an idea of how close we're going to get to the c values versus how close we're going to get to our limiting value. Okay, so we're going to see how the epsilon window and the delta window complement each other. All right, so here's an example. All right, so we're going to take this example and we're going to prove this limit. Using the epsilon delta definition. All right, so this is how you would actually approach it when you do study this in a calculus class. So this problem right here, limit as x approaches 2 of 7x minus 5. Well, so when you start learning limits, the informal definition, we learn the substitution principle. You can just basically take this number 2, plug it in, and so 7 times 2 is 14. 14 minus 5 is 9, and so if you get a real number, that is what your limit is. So the limit is 9, but what gives us permission to actually call it 9? Because the x's are just getting close to 2 from the left and the right, so the y's are approaching 9. So the epsilon delta definition really gives you the opportunity to say, yeah, we can actually say that the answer is 9. But so we want to prove it, and this is our problem here. All right, so it's a linear function. All right, f of x equals 7x minus 5. So the slope is 7, the y-intercept is a negative 5. And so as the x's approach 2 from the left and the right, the y's appear to be going to 9. And so here's a graphic representation. All right, so we want to prove this. Okay, so how do we start when you're actually writing a proof to explain using the epsilon delta definition? Well, you want to use the terms inside the definition here. So we're given an epsilon greater than 0, we need to find, right? We need a delta. Okay, so we need to find a delta that's greater than 0. We need to figure out what our delta is, okay, such that, all right, if 0 is less than absolute value x minus c is less than delta, okay, then the absolute value of f of x minus L is less than epsilon. Okay, so I wrote this out because when you're actually working through the epsilon delta definition, what you need to do first is we need to figure out what our delta window is. Okay, so delta is going to be in terms of epsilon. The delta window is dependent on your epsilon window, so we need to find our delta window. We're going to find it in terms of epsilon, so we are actually going to take our definition here and work backwards to figure out what our delta window is, and then we're going to prove that it works. Okay, so we're working backwards. We're going to take the conclusion right here, the absolute value of the function minus limit less than epsilon, and we're going to see what our delta window is based off of this. All right, so you start by working with the conclusion. Okay, so absolute value, so the function, remember this is our problem here, limit as x approaches, this is c, our function is 7x minus 5 equals our limit is 9. So just make your substitutions here, the function 7x minus 5 goes in for f of x, okay? We subtract from that the limit that we got here, which is 9, right, and that's less than epsilon, okay? And then we can simplify inside the absolute value signs, you can call this 7x minus 14. Negative 5, negative 9 is a negative 14. So just simplifying, all right? Then look at this algebraic expression inside the absolute values. You can factor out a 7. So we're going to factor out a 7, so you have x minus 2 here when you factor out the 7. All right, and you can take the 7 outside the absolute value signs. It's already positive. If it was negative, you would take it out as a positive number. So we can take the 7 out of the absolute value sign. So you have x minus 2 is less than epsilon. And divide both sides by 7, okay? So divide both sides by 7, so you have your x minus 2 is less than epsilon over 7, okay? So now what do we have here? If you look at this carefully, we x minus our c value, x minus the c value is 2, we have the x minus c value, okay? So the x minus c value here, all right, so specifically for this problem, our c value is 2, so we can replace this with 2. So we have our x minus 2 absolute value expression right here. So the implication is, well, okay, what is my delta window? Looks like my delta window is going to be 1/7 of my epsilon window. So my delta window that I needed to find is 1/7, epsilon over 7, it's 1/7 of my epsilon window. So this is what my delta window is, okay? Now we want to, let's go ahead now and actually write our proof, okay? So we want to write our proof actually using the language in the definition, okay? So in the language in the definition, what does the language say? Well, you know, your limit problem, it says for every epsilon greater than 0, okay, there exists a delta greater than 0, all right, such that absolute value, right, x minus c is less than delta, okay, greater than 0, okay, implies, right, that your f of x minus L is less than epsilon. Okay, so this is what it says. So anyways, when you're actually looking at the definition, it's a conditional statement, okay? And so after your word if here, you have the delta expression. So when you're actually doing the proof, you have to start with your conditional statement, okay? So let's go ahead and write the proof. So we're given, and then we have epsilon greater than 0, okay, and we have 0 is less than absolute value x minus c, okay, 2, x minus 2, all right, is less than our delta. And so we have this for, this is how we're going to start, okay, because after the word if, you got to start with that statement. So now what do we have? So you're going to take the x minus 2 absolute value sign, and we're going to use our delta. What did we compute to be our delta for this problem? We computed it to be epsilon over 7. So you're computing it to be epsilon over 7. So you can take the delta and replace it with epsilon over 7 because we did the work over here to figure out what our delta window is. It's 1/7 the epsilon window. We know that epsilon is greater than 0, so I don't have to write this part of the inequality anymore. Okay, multiply both sides by 7, so you have 7 times absolute value x minus 2 is less than epsilon. You can put the 7 back inside, distribute the 7 inside, so you have absolute value 7x minus 14, okay, is less than epsilon. And you can break this up any way you'd want to. The way we need to break it up is to write it back so you have absolute value 7x minus 5, right? That's what the function is, and then we subtracted 9 less than epsilon. So you can see that we figured out what our delta window needed to be, and we went through and wrote the proof, and we're able to bring it right back to where we started. So this is the way that you would actually write out, right? And this is end of proof, all right, that you would write out an epsilon delta explanation of working through a limit. Okay, let's take a look at the graph over here. So what does this represent? Okay, so what does this represent? Our function is 7x minus 5 is a linear function. So it's a green line over here. That's our function. We want the limit as the x's approach 2. As the x's approach 2 from the left and the right. So you have your window. This is your delta window here. This is going to be 2 plus delta. And this is going to be 2 minus delta. That's our delta window over here. Okay, and then let's follow this window up. Okay, so we go up to here, going up to here. Here's our delta window. Okay, and then we're going to move this across. Here's our epsilon window. Okay, so this is going to be 9 plus epsilon. This is going to be our 9 minus epsilon. There's our epsilon window. Okay, so taking a look at the graph over here. Okay, not exactly drawn to scale, but it should be close enough to get across the point across. So take a look at the graph over here. Your epsilon window, all right, and your delta window, look at the relationship between the two windows. According to our calculations, your delta window is 1/7 of your epsilon window. Your delta window is just 1/7 the size of your epsilon window. Okay, or your epsilon window is 7 times the size of your delta window. So it puts the windows, as you approach the C value from the left and the right, as you're approaching your C value from the left and the right, as you get arbitrarily close to your C value from the left and the right, where are the Y's going? It sort of puts a size on that for you. So we can see that our delta window for this problem is 1/7 the size of the epsilon window, okay? And this is how you would write up, you would need to find your delta window, all right, and then you would actually need to use the definition to write your proof to show that it indeed does work to prove. So now we can actually say, yes, the limit as x approaches 2, as the x's get arbitrarily close to 2 from the left and the right, 7x minus 5, the y's are going to 9. They're going to 9, and we prove that we can say that. So here is first example. And let's do one more, just one more for repetition, just to make sure we get it, okay? So let's do a second example, and I'll sketch a graph of the second example also when we get to that. So let me do the second example, and it'll be a limit problem. And we'll go through all this again. And it's another linear problem, so this is going to be a little bit repetitive. Just want to do 2 examples to make sure we have enough. So second example, let's take the limit as x approaches 4. So this is example number 2. We're going to take the limit as x approaches 4. All right, and our function is going to be x over 4 minus 3. So we're going to take x over 4 minus 3 for the function. All right, so take the 4, plug it in. 4 divided by 4 is 1. 1 minus 3 is a negative 2. All right, so we're here. We want to prove this limit. We want to prove this limit using the epsilon delta definition. All right, and it's a linear function again. So as the x's approach 4 from the left and the right, the y's are going to negative 2, and we want to prove that. Okay, so what do we have to do to prove that given your epsilon delta definition? So pretty much we're going to figure out how the delta window depends on the epsilon window. Okay, so the delta window is going to be what size in terms of the epsilon window. We're going to figure that out for this problem. So using the epsilon delta definition, so given our epsilon greater than 0, okay, we need to find our delta, okay? So we need to find our delta, positive delta, okay, such that 0 is less than absolute x minus 4, right? X minus c value is less than delta, okay? Is going to imply absolute value f of x minus L less than epsilon. Okay, so that's what your definition is. That is your formal definition. So we need, first of all, we got to do the work because we need to figure out what our delta window is. We want to find our delta window and how our delta window is with respect to size, with respect to epsilon window. All right, so our delta is always written in terms of epsilon. All right, so we're going to figure out what our delta window is, okay? So we're going to start by taking the function. The function for this one is x over 4 minus 3, okay? And then we're going to subtract the limiting value, which is a negative 2. Set it less than epsilon, okay? And then we're going to do some algebraic maneuvers in here to make this look like x minus 4, okay? So we're going to move from, so when we're doing, just working backwards, doing the work to get our delta. So let's go ahead and do the arithmetic here. So we have x over 4 minus 3 minus a negative 2, so it's a negative minus 1, okay? Less than epsilon, all right? And let's go ahead and factor out a 1/4 here. So factor out a 1/4 because we know that needs to be x. So factor out a 1/4, okay? So that gives us x minus 4, all right? So 1/4 times x is x over 4. 1/4 of negative 4 is a negative 1. 1/4 can come outside, so pull the 1/4 outside, and here's your x minus c value in here is less than epsilon. Multiply both sides by 4. So absolute value x minus 4 is less than 4 times epsilon. Okay, so your delta window in this problem, your delta window here, okay, is going to be 4 times your epsilon window. Your delta window depends on your epsilon. Okay, so delta depends on epsilon here. So this is what your delta window would be. Okay, we can look at a graph. I mean, you can look at a graph so you can see. Let me see if I can draw it freehand a little bit here. So here's the y-axis. So here's a y-axis, I'm drawing an x-axis over here. So this y-intercept is a negative 3 for this problem, okay? And it is it's x over 4, so the slope is 1/4. So it's going to be a line that's not very steep, is it? Okay, so not a very steep line. So when I sketch this, not a very steep line, okay? So this is about what the function looks like, okay? So here's my function here, all right? As the x's approach 4 from the left and the right, as the x's approach 4 from the left and the right, the y's are going to negative 2. So we can put 4 maybe about here, okay? And then the y's are approaching negative 2, okay? So we can put that about here, okay? So here's my negative 2. The x's approach 4 from the left and the right, the y's are approaching negative 2, all right? So our delta window, so our delta window is, however you want to set up your delta window. Here's 4 plus delta, here's 4 minus delta, all right? And so how is that going to affect your epsilon window? Okay, so sketch it down here and sketch it down here. And so here's my negative 2 plus epsilon, and then negative 2 minus epsilon, all right? So here's your delta window here, okay? And here's your epsilon window over there. So according to our calculations, and it's not drawn exactly to scale, but your delta window is 4 times the epsilon window, okay? So your delta window is bigger than your epsilon window. It's 4 times the size of your epsilon window. So as you get arbitrarily close to a c value from the left and the right, but how close, okay? So we want a little bit more precision as that, how close, right? And we still have to write our proof, right? We still have to write our proof. This is a conditional statement. Right, it's an if-then statement. So remember what this says, okay? So we're given, okay, or for every epsilon greater than 0. I'll use that language. So this symbol right here means for every. So for every epsilon greater than 0, okay? Backwards capital E, there exists, okay? So there exists a delta greater than 0 such that, so we just such that, okay? The 0 is less the absolute value of x minus c is less than delta, implies that absolute value f of x minus L less than epsilon, okay? So we want to go ahead and let's verify, because we had to do the work to find the delta window. So now let's go ahead and confirm this, okay? So it's an if-then statement. We need to start with, okay, 0 is less than absolute x minus 4 is less than delta, okay, because 4 is my c value here. Now delta, we know what delta is now. We know that delta is 4 times epsilon. So you have absolute value x minus 4 is less than 4 times epsilon. All right, and I can drop the left part of the inequality because I've got epsilon greater than 0, so I know that the delta is going to be greater than 0. So divide both sides by 4, so that brings the 1/4 back over here. And move the 1/4 inside your absolute value signs. This gives you x over 4 minus 1, okay, is less than epsilon. All right, and then I want to generate my numbers here. So you can write this infinitely many ways, but we want to write it as a way that we can bring back and prove that, yes, we can get back to the absolute value of our function, which is f of x minus 3, minus the limiting value, which was a -2. All right, and so we have proved that this delta window will generate our epsilon delta definition of limit. So here's your end of proof, and this is a little bit, it's more abstract. The topic is more abstract, but it's just a little bit more to, and you practice and try to see it, but this is going to be used so much in your math classes to come. Advanced math classes, we use the epsilon delta definitions all the time to show why things work and when we're writing proofs and so on. So formal definition of limit. This is your precise formal absolute definition of limit. So I hope this video helped. Thank you for watching. Best wishes, good luck with all your endeavors, and thank you again.